Good morning, students. We will wait for 2 minutes, then we will start. So in this chapter, we will start. The weightage is decreased in this year, though the chapter is very big chapter. The weightage is very small. So the questions will be asked on one numerical will be there. And this defect part is newly introduced in the syllabus. In the old syllabus, there was these stoichiometric and non-stoichiometric defects are not there. But this year, these defects are introduced. So there is a more possibility of the questions which will be asked on these defects. So more concentrate more when you are going to study these defects. This is very easy to understand actually. So yesterday we discussing about this impurity defect. So this impurity defect arises when the foreign atoms means these atoms are different from the host atoms actually. It is called as foreign atoms when these are present in the crystal lattice. It is called as impurity defect. So there are two kinds of impurity defect. Impurity is at the impurity is substituted. It is called as substitutional impurity defect. See this example of brass. In this, host is copper molecules or copper particles, and this zinc is a foreign atom. So the impurity is substituted, means host atom is substituted by the impurity. Such type of defect is called as substitutional impurity defect, in which the impurity is substituted. So we are already discussed about this alloy. Brass is an alloy of copper and zinc, in which zinc is impurity and copper is host. Then we are discussing this vacancy through the alloy-valent impurity. So what is meant by this alloy-valent impurity? I will discuss first. These are the alloy-valent. Alloy-valent ions means these ions having the oxidation state different from the host ions. It is called as alloy-valent ions. When these alloy-valent impurities also substituted, so we will take this example. This is if a small amount of SrCl2 impurity is added to the NaCl, actually the host is NaCl. So SrCl2 if impurity is added, so what happens? The added Sr2 plus ions, its oxidation state is +2. So what will happen to this Sr2 plus? It is +2. So these Sr2 plus ions occupy some of the regular sites of Na plus. This Sr2 plus occupies the regular site of Na plus host ions whose oxidation state is +1. So see the oxidation state of Na plus is +1 and oxidation state of Sr2 plus is +2. So there is a different oxidation state here. Sr2 plus is alloy-valent ion. Remember, Sr2 plus ions, these are alloy-valent impurities, or it is also called as alloy-valent ions, whose oxidation state is different than the host. Here host is Na plus, whose oxidation state is +1, and Sr2 plus oxidation state is +2. So what will happen? To maintain the electrical neutrality, what happens? Every Sr2 plus ion removes two Na plus ions. Here we can see here Sr2 plus is added. So one Sr2 plus, if it is added, two Na plus ions are removed. Two Na plus ions are removed. We can check here. Here, one Na plus is ion removed from here, and another Na plus ion is removed here, and one of the vacant lattice is occupied by Sr2 plus ion. So this vacancy is this from here. Two Na plus ions are removed. One is from here and another is from here. But one vacant site is occupied by Sr2 plus ion. The other site of Na plus remain vacant. So this will be remain vacant, and one vacant site is occupied by Sr2 plus. So such type of example is called as vacancy through the aliovalent impurity. Here Sr2 plus is aliovalent impurity. Then next one is impurity is at the interstitial position. It is called as interstitial impurity defect. In this defect, the impurity atoms occupy the interstitial spaces. Now you are familiar with this word interstitial, means in between this vacancy. This is a regular site of the particle. This is also regular site. So this is the interstitial empty space. So this is the impurity. This is the impurity we can see here. This is also the impurity as the interstitial position. This is a very good example of steel. Impurity is not substituted. See here, impurity is not substituted, but impurity is at the interstitial position. This is a very good example of stainless steel. This stainless steel, it is made up of with uh, iron, and here carbon is impurity. So carbon atoms are at the present at the interstitial spaces. This can be asked for 2 marks for the examination. Write the note on impurity defect or interstitial impurity defect. They will mention which impurity defect we have to write. Then this is the last part of this chapter, that is called as non-stoichiometric defects. Again, I am going to show you this classification. See this point defects in which this stoichiometric point defects is completed, vacancy defects is completed, self-interstitial defect, then Schottky defect, Frenkel defect is completed, then impurity defect just completed. There are two impurity defects, substitutional impurity and interstitial impurity. Again, this substitutional impurity vacancy through allovalent, this is also completed. This is also completed. Now we will discuss about this non-stoichiometric point defects. If you understand the stoichiometric point defects, in case of stoichiometric point defect, the ratio of number of atoms remains same. Stoichiometry doesn't changes. But in case of this non-stoichiometric point defect, the stoichiometry will be changed. That is, the ratio of number of atoms of cations and anions will be changed. So see here, the non-stoichiometric defect means what? Directly I will understand the main point. See this number of uh, the ratio. This is the ratio of number of atoms. The ratio of number of atoms here. Number of atoms means the ratio of number of cations and anions is different. And in case of stoichiometric defect, the ratio of number of atoms, it is same. So in this non-stoichiometric defect, the stoichiometry, it is changed. Stoichiometry will be changed. It is important to note that change in stoichiometry does not cause any change in the crystal structure. So if the stoichiometry is changed, there will be no change in the crystal structure. Again, there are two types of non-stoichiometric defects. One is a metal deficiency defect. Metal deficiency in which the deficiency of metal is there. So This defect is possible only in the compounds of metals that show variable oxidation state. Remember, means that metal should show different oxidation state. This is the first condition. Then second condition, in some crystals, positive metal ions are missing. Positive, generally positive metal ions are missing from their original crystal lattice. So what will happen? Extra negative charge is balance. This is a very, very important sentence. The extra negative charge is balanced by the presence cation. This charge will be balanced by the presence cation of the same metal with higher oxidation state than the missing cation. So after this example, you can understand this metal deficiency effect. See, we are going to take the example of NiO. This is a crystal of NiO. We can see here Ni2 plus, O2 minus, Ni2 plus, O2 minus, O2 minus, Ni2 plus, O2 minus. So this is the regular arrangement. But here we can see here Ni3 plus is there, and here also one Ni3 plus is there. So from where this Ni3 plus came, we will understand by this example. So in this NiO compound, one Ni2 plus ion is missing. One Ni2 plus ion is missing from here. See, one Ni2, sorry, this Ni2 ion is missing here. We can see here O2 minus, Ni2 plus, O2 minus. So Ni2 plus, one Ni2 plus ion is missing, and to balance the negative charge, what will happen? Uh, so the deficiency of two positive charges. Ni2 plus means two positive charges are there. So this deficiency is fulfilled by two Ni3 plus ions. This deficiency is completed by the two Ni3 plus ions. Uh, the deficiency of two positive charges is made up by the presence of two Ni3 plus ions at the other lattice sites of Ni2 plus ions. So to fulfill the plus 2 charge, there are two Ni3 plus ions are there. See, we can see here. Here is one Ni3 plus ion, and here is another Ni3 plus ion. So it becomes Ni3 plus, remember. So with higher oxidation state, here it is explained to balance the extra negative charge. The cation of the same metal means Ni, it is the same metal with higher oxidation state. Oxidation state is also changed. Ni2 plus vacancy is created, and its charge is balanced by the two Ni3 plus ions. So this is an example of metal deficiency defect. So the combination of the NiO, it will be changed. So see this combination, it is changed. That's why it is called as a non-stoichiometric defects. Ni is 0.97 and oxygen is 1.0. See, these values are not same. That's why this is called as non-stoichiometric defect. Metal excess defect, in which the metal is in excess. So there are two types of metal excess defects. First one, a neutral atom or an extra positive ion occupies the interstitial position. See this example clearly. In case of the zinc oxide, presents two ways. This is the first type. Zinc oxide presents two ways of metal excess defect. In the first case, in case of this ZnO lattice, one neutral, here is one neutral zinc atom. It is present at the interstitial position. So this is a first type of metal excess defect. In case of this second case, when this zinc oxide is heated, when this ZnO is heated, what will happen? It will decomposes and it will produces Zn2 plus ions plus 2 electrons. So these Zn2 plus ions and these two electrons, we can see here, this is the Zn2 plus ions and this is the first electron. This is the second electron. So when this ZnO plus, sorry, zinc oxide is heated, it will decomposes to Zn2 plus and 2 electrons. So the excess of this Zn2 plus, it is trapped at the interstitial site of the lattice, and the electrons are also occupy the interstitial position. So in this, see the stoichiometry, it is changed. The stoichiometry of the zinc oxide, it will be Zn 1 plus X and oxygen 1.0. See this stoichiometry means the ratio, it is different. This the ratio of the cation and anion, it is different. So it is also the good example of non-stoichiometric defect, metal excess defect, in which the metal is in excess. There are two types, two cases in this zinc oxide. First, this neutral atom, we discuss about this first type, and the second type is by anion vacancies. This is a newly introduced in your syllabus, the anion vacancies. It is also called as color or F centers. So this is a specific type of defect which is very, very important for the examination point of view. This type of defects imparts color to the colorless crystals. Means color is appeared to the colorless crystal. We will see this one example is given in detail. When NaCl crystal is heated in the atmosphere of sodium vapor, so this is a crystal of NaCl. If it is heated in the atmosphere of sodium vapor, what will happen? Sodium atoms are deposited on the crystal surface. Na plus or sodium atoms are deposited on the surface of the crystal surface. Also, Cl minus ions diffuse to the crystal surface, creating vacancies at their regular sites. So what will happen to this Cl minus ions also diffuse on the crystal surface, creating vacancies. But these sodium atoms do not create vacancies. This Cl minus creating vacancies. This Cl minus, it will combine with Na, because both are on the surface and they will form NaCl. So Na particles, sodium particles already, these are deposited on the crystal surface. The Cl minus also deposited or diffuse on the crystal surface, but the Cl minus create vacancies and NaCl will be formed. So this NaCl, it is formed by releasing one electron from the sodium atom. So it is shown here. This sodium chloride releases one electron. So this extra electron or released electron occupy the vacant sites of the anion. So this electron, it is we can see in this diagram. This is electron released from sodium chloride. This electron we can see. This is a released electron. It will occupy the vacant size created by the Cl minus ions. This vacancy is created by this Cl minus ions. So this extra electron will occupy the vacancy created by the Cl minus ions, and due to this electron, what will happen? See, so this the anion vacant, this vacancy is created by the anions. So the word is used here. The anion vacant site occupied by the electrons are called as F centers or color centers. It is called as F centers or colored centers. So NaCl becomes shows yellow color due to the formation of F center. So this is called as F center. Remember, F center. The crystal of NaCl has excess of Na because it is deposited on the surface. The non-stoichiometric formula of NaCl is Na 1 plus X and Cl is 1.0. We can see the ratio here. Na is 1 plus X and Cl is 1.0. So it is also the very good example of non-stoichiometric effect. It can be asked for 2 marks. Each defect is very important for the examination point of view. So this is a non-evaluative deleted syllabus, electrical properties of solids 1.9. This entire 1.9 is deleted: conductors, insulators, semiconductors, then band theory, then conduction band, valence band, band gap, the metals, what is mean by metals, and what is mean by insulators, what is mean by semiconductors. Again, there are two types of semiconductors: it's extrinsic semiconductors, intrinsic semiconductors, n type semiconductor. Detailed notes I have given in this chapter. Those students who want to uh, prepare for the competitive examinations, JE examination, NEET examination, and CET examination, go through these notes, because I have taken these notes from 3 to 4 different types of textbooks and also reference books: P type semiconductor, N type semiconductor. In detail, I have explained magnetic properties. There are three magnetic properties: diamagnetic solids, then paramagnetic solids, ferromagnetic. Some of the part is also repeated in physics also, and all the numericals are given here. All the numericals from the exercise, all the numericals are given here. So this chapter is completed, and these are also the questions asked in previous board examinations. Define anisotropy, distinguish between crystalline solid. Now this part is non-evaluative, so such type of questions will be not asked this year, because this crystalline solids and amorphous solid, this part is removed. But they can ask this question: what is the ratio of octahedral holes to the number of anions in hexagonal closed packed structure? This is 1 mark question. This is March 2019. This is July 2019. Give the relation between radius of the atom and age length in BCC. BCC structure, it is asked for 1 mark. Then classify the following solids: diamond, NaCl, P4 molecule, brass. It is asked for 3 marks. What is Schottky defect? Schottky defect is for 1 mark, and this classification, it is asked for 2 marks. So such type of example, so questions will be asked for the examination. The number of atoms per unit cell of BCC, this is asked for 1 mark question. BCC, 2 atoms are present, remember. Classify the following solids into different types. Again, it is asked for 2 times. See, here also it is asked for the classify the solids. Here it is also asked for the examination, March 2020, silver, then P4, diamond, NaCl, it is asked for 2 marks. And one numerical is asked here, unit cell of metal age, it is asked for 3 marks. So this chapter is completed here. It is most of the part is deleted in this chapter. So I will unmute all students. If you want to discuss anything, you can ask. अनम्यूट केले सगळ्यांना मी. ज्यांना काय विचारायचंय ते विचारू शकता. विचारायचंय का कोणाला काय? कारण हे सगळं परीक्षेत बोर्डाला विचारणार नाहीये. दिस इज अ नॉन इव्हॅल्युएटिव्ह पार्ट. कुठून? 1.9 1.9 से लेके एंड तक. दिस वन, electrical properties of solid. This 1.9 is deleted part. But some students are preparing for the different competitive exams. For these students, I have given these notes. What is mean by conductors, insulators? This is very easy. We can go through it. You can understand. कुणाला काय बोलायचंय का? दुसरा चॅप्टर सुरू करायचंय मला. येस, हितेश सुतार.
यातले इम्पॉर्टन्स काय विचारू शकतील ते?
इम्पॉर्टंट सांगू का? हे बघा, क्लासिफिकेशन तुम्ही जर बघितलं असेल तर क्लासिफिकेशनवर बऱ्याच वेळा प्रश्न विचारलाय. क्लासिफिकेशनवर मी येतो, 1 मिनिट. सुरुवातीपासून आपण जरा चेक करूया. हे क्लासिफिकेशन म्हणजे की असं चार्ट विचारणार नाहीत तुम्हाला काढायला, लक्षात घ्या. ड्रॉ द चार्ट ऑफ क्लासिफिकेशन ऑफ सॉलिड्स हे पुस्तकात पण दिलेलं नाहीये. फॉर द अंडरस्टँडिंग पर्पज आय हॅव गिवन दिस क्लासिफिकेशन ऑफ सॉलिड्स, बट द एक्झामिनर कॅन आस्क द क्वेश्चन ऑन this one: ionic solids, covalent solids, then molecular solids and metallic solids. So these are the examples are also given. So remember these examples: ionic solids, NaCl, then K2SO4. All the ionic salts are included in these ionic solids. Then covalent, diamond, quartz, phosphorus. See, this phosphorus many times it is asked for the examination. It is a molecular solid. Then metallic: sodium, potassium, iron, aluminum, gold, silver, all these are metallic crystals. So many times this classification is asked for the examination. Also some extra examples I have given here. This SiO2 quartz, then diamond, all these are covalent or network solids. See the silver, it is metallic. Silver, gold, copper, iron, these are the metallic solids. Ionic, all the salts. Then hydrogen bonded H2 ice, polar HCl, SO2. Then this is a non-polar H2, I2, CO2.
डिफरन्सिएशन मध्ये पण विचार.
डिफरन्सिएशन नाही विचारणार, पण हे विचारतील, त्याचं क्लासिफिकेशन विचारतील. डिफरन्सिएशन हे काढून टाकलेले आहे बघा, मी सुरुवातीपासून सांगतो, हे परीक्षेला नाहीये तुम्हाला. क्रिस्टलाइन सॉलिड्स, अमॉर्फस सॉलिड्स हा पार्ट काढून टाकलेला आहे. दिस इज डिलीटेड. म्हणजे ह्या वर्षी तर याच्यावर प्रश्न विचारणार नाही, नेक्स्ट इयरला विचारतील. तुम्हाला खूप सोपं केलेले, याच्यावरती प्रश्न विचारणार नाही. हे आयसोमॉर्फिझम, पॉलिमॉर्फिझम करून ठेवा, याच्यावर 100% प्रश्न विचारतील 1 मार्काला, म्हणून तर ते ठेवलंय. लक्षात घ्या, सिलेबस ज्यावेळेस आम्ही डिलीट करत होतो त्या कमिटीत मी पण होतो, तर लोकांचं, बाकीच्या शिक्षकांचं असं म्हणणं होतं की हे आपल्याला ठेवायला पाहिजे. याचा अर्थ काय असतो लक्षात घ्या, की त्याच्यावर प्रश्न विचारतात. ह्या गोष्टी आता सांगायला डिटेलमध्ये सांगायला नको. हे का ठेवले, कारण याच्यावर प्रश्न विचारणार तुम्हाला. व्हॉट इज मीन बाय आयसोमॉर्फिझम, व्हॉट इज मीन बाय polymorphism. That's why it is kept, it is not deleted. Remember, this is deleted. Anisotropy, isotropy, it is deleted, I think, but this isomorphism, polymorphism, it is not deleted. त्याच्यानंतर हे तर काढलेलंच आहे. क्रिस्टलाइन सॉलिड, it is removed. Amorphous solid, it is also removed. But this property is anisotropy, isotropy is also deleted. But this isomorphism, polymorphism, it is not deleted. Remember, this is deleted. This classification we can, at a glance, we can remember these 2 slides. With these 2 slides, we can understand all the classification: ionic solids, crystalline, ionic, covalent, and molecular and metallic solids. So all these slides, it is covered in these 2 slides. At a glance, we can read at the time of examination. Then I'm coming to this is not asked for the exam, never. What is mean by lattice and what is mean by basis. But unit cell can be asked for the exam for 1 mark. What is mean by unit cell? Then these diagrams, never it is asked for the examination. So don't worry about the diagrams. But they can ask these definitions. What is mean by primitive unit cell? What is mean by body-centered unit cell? What is mean by face-centered unit cell? Diagrams are not expected from the students. Diagrams are not expected from the students. This can be asked for MCQ. How many types of crystal systems are there and how many Bravais lattices are there? This is also not expected from the student. Angles are also not expected, but for the competitive examination, student have to remember the angles also. For that, I have given one chart. म्यूट करा, कोणाचा तरी माईक चालू आहे. हे तुम्हाला काढायला विचारणार नाहीयेत. No any examiner will ask to draw the structures, but we have to remember what is meant by cubic, orthorhombic, tetrahedral. By this chart, but by this table we can remember. So this table is very important to remember the edge length. Edge length. How to remember this? I have given also the idea. First cubic rhomboedral, we have to write down A is equal to B is equal to C. Here is also A is equal to B is equal to C. Then we have to write this tetragonal, A is equal to B, not equal to C. So this and this hexagonal, it is same. A is equal to B, not equal to C. And remaining 1, 2, 3, it is same. Orthorhombic, monoclinic, and triclinic. So we have to remember this short form I have prepared. We can prepare any type of short form. And for the angles, I have given the idea. First three angles are same. Alpha, beta, gamma is 90. Alpha, beta, gamma is also 90. Alpha, beta, gamma is also 90 degrees. Then here we can see these angles we have to remember. These 1, 2, 3, 4. So this can be asked for the MCQ purpose or competitive examinations. It will be asked. Then this will be asked for the definition purpose. What is meant by simple cubic, body centered cubic? The screen is visible. Yes, anyone tell me screen is visible?
Yes, sir.
Because there is some internet problem. In case of body centered cubic unit cell, there are two particles. So remember the particles only. How the particles are calculated, no any examiner will ask the question. But we have to remember in case of BCC, there are two particles. In case of simple cubic, there is one particle. And in case of face centered unit cell, there are four particles. So remember these particles, these are required for solving the numericals. Then this relationship, it will be also not asked for the examination. This is for your solving the numericals. This relation, it is for solving the numericals. So this numerical, it is based on this formula density. 100% one numerical will be there in this chapter. It will be either calculating the density or either calculating the this close packing dimensions in which the coordination number which will be asked for the examination, or write the note on square close packing, write the note on hexagonal close packing. It will be asked on the close packing, but this is not expected from the student point of view. These diagrams are not expected. So don't worry about this chapter. It is very easy, and the difficult part, it will be not asked for the examination. Then this will also not ask for the examination to the other diagrams. Student, from the student point of view, it is expected to know the coordination number. What is mean by coordination number? What is mean by close packing? So this is expected. Remember this packing efficiency, these values can be asked for the MCQ purpose in case of simple cubic unit cell, in case of body centered cubic unit cell, in case of face centered cubic unit cell. Uh, these values are important for the examination, and this can be asked for 2 marks. Packing efficiency is very important, because how this packing efficiency it is calculated, it can be asked for the exam. Then only 2 packing efficiencies are there, in which a simple cubic unit cell and body centered cubic unit cell. This is deleted. This is in case of face centered cubic unit cell, this part is non-evaluative part. So this is deleted for this year only. So only we have to remember the 2 packing efficiencies. Number 1 is simple cubic lattice, and number 2 is body centered cubic lattice. Remember these 2 values: 52.4 for simple cubic and 68%. This is space occupied for the BCC. This is a non-evaluative. 74. This part is non-evaluative for this year. Then these are the 2 formulas. Only remember these formulas. If you want to calculate the number of particles, we have to remember this formula: xn divided by rho a cube. This is a formula for calculating the number of particles. And to calculate the number of unit cells, we have to remember this formula, x divided by rho u cube. Only the difference is n. So if the number of particles are asked, we have to use this formula, and the number of unit cells it is asked, we have to use this formula. And this is another formula it is given, the number of unit cells in volume V. If the volume is given, we have to use this formula, V divided by A cube. So total there are 4 formulas in this chapter. This is number 1, this is number 2, this is number 3, and I will show you this relation to calculate the density. This one. So these 4 formulas very important for solving the numericals. And also I will show one chart. We have to remember this chart. You got that chart. These values for simple cubic and body centered cubic. These values we have to remember. This R values we have to remember 0.500A, and this is a volume of one particle, and this is a total volume occupied by the particle. So remember for this 1 and 2, simple cubic and body centered cubic. So these values only we have to remember for solving the numericals. So if uh, all these values are known, we can solve any numerical. So all these numericals are depend upon these formulas. And the defects are very important. So this is the important uh, points I have discussed. So any doubt? Again, we have to start the second lecture. We will start the new chapter, thermodynamics. So I am going to stop here. Again, we have to join at what timing I have given?